In this video, we're going to talk about curvature. Now, before we give the formal definition of what curvature is, let's look at what the idea is. So let's look at this picture down here. So we have a curve. Now, I've drawn the curve here in 2 space, but you could draw a curve that's moving through 3-dimensional space. But you can think of this curve maybe almost like it's a road, okay, that you're driving along, right? So notice if you're driving along this road, notice the curve is kind of bending a little bit here. The road is bending a little bit here, but not very much. Whereas when you get over here, it's really winding around a lot. And so what we say is that the road here has more curvature over here than it does over here. Okay, it's bending more quickly over here than it is over here. So we say we have more curvature here, we have less curvature here. Now, is there any way to make this idea mathematically precise? Well, yes, there is. So let's go to a definition. And the definition says if C is a curve in 2 space or 3 space that is parametrized by arc length. Okay, and that's going to be key here for this definition. We have a curve that's parametrized by arc length, so meaning it's being traced out at a constant, rate of 1 unit per second. Then the curvature C, denoted by kappa, okay, it looks like a K. If I accidentally say K, I mean kappa. Kappa, or kappa of S, is defined by this. So kappa of S is the norm of T prime of S, which is equal to the norm of R double prime of S. Now, we're using the letter S here instead of T because we're talking about an arc length parameterization. So let's recall that T of S is really R prime of S. And so T prime of S will be R double prime of S. Okay, now just remember though, T is the unit tangent vector. Okay, but normally if you have a curve that's not parametrized by arc length, which most curves probably won't be, then T of T, the unit tangent vector, will be R prime of T divided by the norm of R prime of T. So R prime of T will just be a tangent vector, but if we want to get a unit tangent vector, we have to divide it by its length. But if you have an arc length parameterization, then all of the R primes are all going to have a norm of 1, so we don't need to divide by the norm of R prime of S. Okay, so this definition here of curvature has to do, it works when we have a curve that's parametrized by arc length. So let's look at what this means kind of geometrically here. So notice that the curvature at a particular point is a measure of the sharpness of the bend of the curve at that point. So remember here, kappa of S is the norm of T prime of S. Now remember, T is a unit tangent vector at each point. Now this curve here is really just a straight line, and notice the tangent vectors, the unit tangent vectors are all pointing in the same direction. So if we want to look at T prime, right, how fast are these T's changing? Well, they're not changing at all. Okay, for a straight line, T prime is going to be 0, right? The 0 vector. So this straight line doesn't have any curvature, or the curvature is 0. Now, if we have a curve here like this, where it's bending a little bit, then if we look at a few of these unit tangent vectors, we've drawn 3 of them right here, notice that as we go from this point to this point, the tangent vector has changed a little bit. It's changed directions a little bit. Of course, they still all have length 1, but it's changed from pointing this way to pointing just a little bit further to the right. And then here it's changing just a little bit. So this does have some curvature, right? So because the T is changing, right? So T prime has to do with the rate of change of T. How fast is T changing? Okay, and notice that it's changing fairly slowly. So what we'd say is that this has kind of a small curvature. Okay, this curve. Whereas this curve over here, it's bending. In fact, it's bending more quickly, right? As we move from here to here, the unit tangent vector has really changed direction a lot from pointing this way to pointing this way. And when we move over here, it's pointing way this way. It's completely different than when we started. So this curve, as we're moving along, those tangent vectors are really changing a lot, right? They have a bigger derivative, right? So if we look at the norm of the derivative, it's going to be bigger. So this has a bigger curvature. By the way, this C almost looks like it's a portion of a circle. And by the way, maybe this C is a portion of a circle as well. It turns out that if you have a circle, the smaller the radius, the bigger the curvature is going to be. But if you have a big circle, imagine a circle even like the size of the Earth, right? Maybe like the equator of the Earth. Well, as you're walking along the equator, you don't notice much bend, right, to the surface of the Earth, right, because it's such a big radius that the curvature is very, very small. Okay, but if you have a small circle, it will have a bigger curvature. Now again, you don't have to have a circle. You could have just some curve like this, and at different points along the curve, you're going to have different curvatures. Whereas for a circle, it'll have a constant curvature. No matter which point you pick, it'll have the same curvature. Okay, but let's suppose, though, we're in the situation where we have a curve that's not parametrized by arc length. Okay, how could we find its curvature at a particular point? So remember, this formula up here, and this is key here, this formula only works if we're talking about a curve that's parametrized by arc length, right? Notice we're using s's here instead of little t's. Okay, well, in that case, though, when we have just a general curve that's not necessarily parametrized by arc length, which would be most curves that you can write down, if r of t is a smooth vector valued function in 2 space or 3 space, then for each value of t at which t prime of t and r double prime of t exist, the curvature kappa can be expressed as either this or this. So kappa of t is the norm of t prime of t divided by the norm of r prime of t. Okay, or it could be written like this: the norm of r prime of t cross, so this is a cross product of r double prime of t divided by the norm of r prime of t quantity cubed. Okay, now these, I did not show you here how we derive these formulas, but you can look in the book, or you can maybe try to figure it out for yourself. Where do these formulas come from? Now, it turns out, though, that this second formula is usually a little easier to apply than the first formula. But on the other hand, here we're using cross products, so we need to have our vector valued function be a function in 3 space, okay, instead of 2 space, right? Because you can't cross vectors that are in 2 space. You can only cross vectors in 3 space. So to use this second formula in 2 space, we have to first write the 2 space function, so r of t equals x of t comma y of t, as the 3 space function x of t y of t 0. Okay, where you have a 0 k component. Okay, so let's do an example. So the graph of the vector equation r, or this probably should say r of t, equals 2 cosine ti plus 3 sine tj, so notice this is in 2 space here, is an ellipse. Okay, and I've actually drawn the ellipse right here. Okay, where t runs from 0 to 2 pi. Okay, so I think t equals 0 would correspond to this point. Okay, if you plug in 0 for t, you'd be at 2 comma 0. T equals pi over 2 would correspond to this point, and then t equals pi would be here. T equals 3 pi over 2, and so forth. But as t runs from 0 to pi, this curve would be traced out, and it would do one complete revolution here. Okay, but it's an ellipse. Okay, find the curvature of the ellipse at the endpoints of the major and minor axes. So just to recall, the major axis is the bigger axis, right? It's the axis that would have the foci. So every ellipse would have 2 foci. So these would actually be along the y-axis in this case. And then this x-axis in this example would be the minor axis. Okay, so the question is, what's the curvature right here? Okay, at 0 comma 3. What's the curvature there at 2 comma 0 and at these other 2 points over here as well? Okay, well, to find the curvature, we're going to use this formula here. Kappa of t equals this. Okay, this is what we, our theorem here. Okay, so to do that, though, we need to find r prime and r double prime. Okay, so let's do that. So here's r of t is our original one. I've written it in bracket notation. 2 cosine t, 3 sine t, 0. Now notice I put a 0 for the kth component. Okay, because we're in 2 space and we're going to try to do a cross product, we need to have our vector value functions actually be in 3 space. Okay, now r prime, we just take derivatives. So we're going to get negative 2 sine t and 3 cosine t 0. And then r double prime, take another derivative, and this is what we end up with. Okay, so if we do the cross product of r prime with r double prime, okay, r prime cross r double prime, we write this matrix here with the I, j, and k, and we put the r prime right here in the second row, right? Negative 2 sine t, 3 cosine t 0. And we put the r double prime down here, negative 2 cosine t minus 3 sine t 0. Okay, so how do we do this determinant of this matrix? Well, notice we're going to get a lot of zeros. In fact, when we do this, when we have a 2-space situation where we have zeros here, you're going to, the I and the j will always be 0, because think about this. What is the ith component going to be? Well, it's 3 cosine t times 0 minus 0 times negative 3 sine t. Well, it's really 0 minus 0. Okay, and then with the j, we have minus, well, again, we're going to have something times 0 minus 0 times something. So we're going to get another 0. Now, what about the kth component? Well, to do the kth component, we're going to do plus k times, well, what's it going to be? It's going to be negative 2 sine t times negative 3 cosine t, so that'd be positive 6 sine squared, minus a negative 6 cosine squared. So minus a negative 6 would be positive 6 cosine squared. So we have 6 sine squared plus 6 cosine squared, but of course that's just 6 times the quantity sine squared plus cosine squared, but sine squared plus cosine squared would be 1. So this whole thing is just 6. Okay, so we have 0, 0, 6. Okay, or just 6k. That's our vector. So that turned out pretty nicely here, just 6k. All right, so kappa of t was defined to be the norm of this vector that we just found, okay, 0, 0, 6, which is going to be really just 6. Think about it, the length's going to be 6. But if you want to write it out, it's the square root of 0 squared plus 0 squared plus 6 squared. So it's going to be the square root of 36, which is 6. Okay, but in the denominator, we have r prime of t cubed. Now, r prime of t was this, the norm of r prime of t. R prime of t was this, so we have the square root of this squared plus this squared plus this squared. Now, this squared is going to be 4 sine squared t. That's what we've written here. And this squared is going to be 9 cosine squared t. And of course, 0 squared is going to be 0. I didn't even write that in. But we have the square root of that, and then that thing's being cubed. Okay, so if we simplify this, the numerator is 6. The denominator, well, we have a square root of something and then cubed. It's like really taking it to the 3/2 power. So we have 4 sine squared plus 9 cosine squared to the 3/2 power. Okay, again, with a square root and then cubed, it's going to be like the 3/2 power. Okay, so what's kappa of 0? Now, why did I pick 0? Well, because we're trying to find when t is 0, we would be at this point here. So we want to find the curvature right here at this point. So that happens when t is 0. So kappa of 0 is going to be what? Well, if we plug in 0 here, we have a formula for kappa of t. If we plug in 0, well, sine of 0 is 0, and cosine of 0 is 1. So we have 6 over 4 times 0 squared plus 9 times 1 squared. Okay, all raised to the 3/2 power. So inside the parentheses here, that's just 9. So we have 6 over 9 to the 3/2. Now 9 to the 3/2, the way you figure that out is you do the square root of 9 and then you cube it. Okay, the square root of 9 is 3, and 3 cubed is 27. So we have 6 over 27, where if you reduce that, divide a 3 out of the numerator and denominator, you get 2/9. So the curvature right here, at this point here, is 2/9. Now, by the way, the curvature over here is also going to be 2/9. You can kind of see that by symmetry. So I said similarly, kappa of pi is going to be 2/9. And you could actually figure that out directly, though, just by plugging in the pi here for here and here. Okay, but you're going to get the same thing, and it makes sense that you'd have the same curvature here as you do here. Now, it looks like it's bending a little more quickly right here, though. Okay, and here. So I'd expect the curvature to be more right here than it is here. Okay, it's bending more rapidly or more sharply right there. Okay, so what's kappa of pi halves? Well, plug in pi halves everywhere you see a t. Now, sine of pi halves is 1, and cosine of pi halves is 0. So what we get in the denominator down here, when we plug in pi halves for t, will be 4 times 1 squared plus 9 times 0 squared. Okay, all to the 3/2. Okay, so inside the parentheses here, now will just be 4 this time instead of 9 like we had up there. So we have 6 over 4 to the 3/2. Now 4 to the 3/2 is 8, right? Because you take the square root of 4, which is 2, and then you cube it, you get 8. So 6/8 or 3/4, that's the curvature at pi halves. And similarly, at 3 pi halves, we're going to get curvature of 3/4 as well. So notice the curvature here was 2/9. The curvature here is 3/4. 3/4 is bigger than 2/9, right? 2/9 is just 0.22222, right? And 3/4 is 0.75, right? So you have a bigger curvature here than you do here. Okay, and again, down here at 3/2 pi, you get the same curvature as you do up there. Okay, now it turns out that it can be shown that a circle of radius a has a constant curvature 1 over a. So what this really means is that if you have a circle, the bigger the radius is, the smaller the curvature will be. And I just mentioned that. So for example, if you have a circle of radius 10, the curvature would be 1/10. Okay, if you have a circle of radius 100, the curvature would be 1/100th, right? The bigger the radius, the smaller the curvature. Okay, if you had a radius of 1/2, the curvature would be 2. Okay, 1 over 1/2. Okay, so the smaller the radius, the bigger the curvature. And if it's a circle, it doesn't matter which point you pick on the circle, it's going to have the same curvature, right? It'll have a constant curvature for a circle. Okay, for a general curve, though, not necessarily a circle, a curve that's just winding around, we define the radius of curvature, rho, at a point P on the curve to be the reciprocal of the curvature. So rho, or the radius of curvature, is 1 over kappa. Okay, and I'll mention what's in parentheses here in a second. But let's look at this picture. Okay, we have this curve, okay, in black, that's winding around, and it doesn't really say which direction the curve is going, but actually it doesn't matter as far as the curvature goes. It doesn't matter which direction the curve is being traced out. So the question is, at this point P and at this point P, what's the curvature? Okay, so if we're at a point P like this, notice the curve is not bending quite as rapidly here as it is over here. Okay, now at this point P, though, we have what's called a radius of curvature and a circle of curvature. Okay, so in fact, in 2 space, if a curve C has non-zero curvature at a point P, then the circle of radius rho, so that that shares a common tangent with C at P and centered on the concave side of the curve at P, is called the osculating circle, or the circle of curvature at P. Now that's kind of a mouthful, but what does that really mean? Well, it means at this point P, really any point P, we can draw a circle, sort of a circle of best fit. Okay, that fits the curve best. Notice this circle really hugs the curve real nicely right there at this point P. Okay, and we need a fairly big circle to make it hug nicely, right? Have a fairly big radius of curvature here. Okay, this is called the circle of curvature. Now over here we have a smaller circle, okay, that kind of hugs the curve real nicely right here. It has a real nice snug fit right there. Okay, now this is a smaller curvature, a smaller circle, but the radius of so the radius of curvatures is smaller than the radius of curvature here. These would be the radius of curvature, would be this radius of these circles. But the curvature is the reciprocal of the radius of curvature. So in other words, at a point where you have a big circle of curvature, you have a smaller amount of curvature. Okay, the curvature is smaller. Whereas if you have a place where the curvature is bigger, you have a smaller radius of curvature, right? A smaller circle of curvature. Right? Notice the curvature here is bigger than here, but the circle of curvature is smaller. Right? And that makes sense because the radius of curvature is the reciprocal of the curvature. Okay, and by the way, let's look at this example that we just looked at here. This example right here where we had this ellipse here. If we want to draw in those circles of curvature, well, what are they going to look like? Well, notice, remember up here we had the curvature was 3/4, right? We had calculated the curvature right here to be 3/4. So if we put a circle right here with a radius of 4/3, right? The curvature is 3/4, but the radius of curvature would be 4/3. This circle will snugly fit that function, right? That would be a circle of best fit right here. Okay, so but notice over here, where it's not bending as rapidly as it was there, remember we had a curvature of 2/9, so the radius of curvature would be 9/2, right? 4.5 would be the radius of curvature. And notice this circle of curvature here is much bigger. Okay, but again, it fits it very well. If at this point we had picked a smaller circle there or a bigger circle, it wouldn't fit so nicely. Okay, this circle is sort of the circle of best fit there. Okay. All right, so let's do one final example here. Find the curvature and radius of curvature of r of t equals 3 cosine t, 4 sine t, t. Okay, at t equals pi halves. So I've drawn in this curve here. Okay, so here's our r of t. I've drawn in the curve. Now, it turns out this looks kind of like a circular helix, which we've done several examples of a circular helix, but it's actually not a circular helix. It's what's called an elliptical helix. So basically, the idea is if you were to kind of maybe think of this curve as being like a spring or something like that that's winding around, well, if you press the spring down so that it's flat in the xy plane, it would actually not give you a circle in the xy plane. It would give you an ellipse. Right, notice we have the 3 and the 4. They're not the same constant in front of these. So actually, along the y-axis, this would go out 1, 2, 3, 4. Okay, and back 1, 2, 3, 4, and then on the negative part of the y-axis. And then for the x-axis, but it would only go out 1, 2, 3. Okay, and then back in the negative part of the x-axis, it would go -3. Okay, so it's not really winding around a cylinder, it's winding around a type of elliptical type cylinder. Okay, but this curve is winding around like this. And the question is, at this point, pi halves, what is the curvature? Now, I just realized I think I made a little mistake here, because if we plug in pi halves, actually it's not 3, 0 pi halves, I think it's 0, 3 pi halves. Because if we plug in pi halves, cosine of pi halves would be 0, whereas sine of pi halves would be 1. So actually it's not even 0, 3, it's 0, 4 pi halves. So this point should be 0, 4 pi halves. Okay, whatever, doesn't matter. The question is, at this point when t is pi halves, what's the curvature? Okay, so at 0, 4 pi halves, what's the curvature? Okay, so how do we find this? Well, we have r of t is this, r prime of t is this. Okay, we take the derivative. Okay, notice the derivative of t is 1. Okay, r double prime of t, take the derivative again. Notice the derivative of 1 is 0. And we derivative of 4 cosine t would be -4 sine t, and so forth. And so again, we need to figure out r prime cross r double prime. Okay, so let's put I, J, K. And so r prime would be, well, put the components of r prime right here. Notice we have a 1 there. Put the components of r double prime right here. Okay, if we take the determinant of this matrix, well, we're not just going to get 0 for I and 0 for j, because we don't have a planar curve in the xy plane. It's winding out in 3 space. So what do we get? Well, what's the ith component? Well, we do 4 cosine t times 0, and that's going to be 0, minus a -4 sine t times 1. So that minus negative is going to end up being +4 sine t with the I. Now with the j, we have minus something times j. Remember, there's a minus in front of it. But with the j, we have this times 0. So that's 0 minus 1 times negative cosine t. So it's going to be +3 cosine t. Now we still have that minus out front. Okay, and finally, with the kth component, we have this times this. So it'll be +12 sine squared minus a -12 cosine squared. Okay, and minus a negative is going to be positive. So 12 sine squared plus 12 cosine squared, that's just 12. Okay, so we have 4 sine t minus 3 cosine t, 12. Okay, that's our r prime cross r double prime. Okay, so our kappa of t is going to be the norm of that. So the norm of this thing divided by the norm of r prime cubed. Okay, so the norm of this thing, that's going to be in the numerator, that'll be the square root of 16 sine squared, right, this squared, plus this squared, which would be 9 cosine squared, plus 12 squared, which is 144. Now let's remind ourselves r prime was this. So if we take the norm of r prime, it's going to be the square root of 9 sine squared plus 16 cosine squared plus 1 squared. Okay, and that's what I've written here, the square root of 9 sine squared plus 16 cosine squared plus 1. And now we are also cubing that. Okay, so we have this. So that's our kappa of t. Now what about kappa of pi halves? Because pi halves will take us to this point, which remember is 0, 4 pi halves. I accidentally wrote that there. Okay, so what is the curvature right there? Well, if we plug in pi halves everywhere we see a t, now sine of pi halves will be 1, and cosine of pi halves will be 0. Okay, so we plug things in, we're going to get 16 times 1 squared plus 9 times 0 squared plus 144, and we have the square root of all that. So that's the square root of 16 plus 144, that's the square root of 160. Now, down in the denominator, again, sine of pi halves is 1, cosine of pi halves is 0, so we're going to get 9 times 1 squared plus 16 times 0 squared plus 1. So this will just be the square root of 10, right? 9 plus 0 plus 1. But then we're cubing it, so we have the square root of 10 cubed, which is really 10 to the 3 halves. Now we could leave our answer like this, but this actually simplifies really nicely. The square root of 160 is like the square root of 60 times 16 times the square root of 10. And 10 to the 3 halves is like 10 to the 1 times 10 to the 1 half. Right? 10 to the 1 times 10 to the 1 half would be 10 to the 1 and 1 half. Right? 10 to the 3 halves. Right, taking something to 3 halves is like doing that thing times the square root of that thing. Okay, but notice the square roots will cancel, and we just have the square root of 16 over 10, but the square root of 16 is 4, so we have 4/10 or 2/5. Okay, so that's the curvature is 2/5 right there. Okay, now the question asked us, what is the curvature? Find the curvature and the radius of curvature. Well, if the curvature is 2/5, what will the radius of curvature be? Well, t equals pi halves at this point. The kappa, okay, or kappa of pi halves is 2/5. So rho will be 1 over kappa, so 1 over 2/5, which is 5 halves. So the radius of curvature will be 5 halves, and the curvature will be 2/5. Okay, and again, I made this mistake. This point is actually 0.4 pi halves, but that doesn't affect our final answer here. Okay, so that's the idea of curvature of a curve that's in 2 space or 3 space.